What I want to go through in this is just review mainly integrals. So at the end of Calc 1, you would have learned about indefinite integrals and definite integrals. Well, what's the difference? An indefinite integral is the one where you found an antiderivative. You have the plus c, the arbitrary constant. A definite integral, you got a definite finite answer to it that represented an area, right? That's kind of the extent of what you usually learn in a Calc 1 class. So one of the things that you want to be sure that you're totally solid with to begin with is what the fundamental theorem of calculus is. So this is basically telling you how you evaluate a definite integral. That's what that is. So when you see this notation right here without the limits of integration, f of x dx, that's an indefinite integral right there. So that's giving you an antiderivative. So let me ask this question. Okay, maybe you hadn't done a calculus problem in a month. If you get an answer to an indefinite integral, how do you tell you're right? You take the derivative and see if it takes you back to the beginning. That's why it's an antiderivative. It's the opposite process. Okay, but when you have a definite integral, then you're putting some sort of limits of integration on like this. Usually we say like from a to b or something like that. So what you're doing is you're taking that antiderivative, and then what you're doing on that is you're evaluating that like this. So typically the way this is stated, this is the main thing I want to look at is this right here, is if you're doing a definite integral, that's what that represents. The capital F, that stands for antiderivative. So that just means anytime you do an integral, like I said, you can tell it's right, okay, by doing the derivative. That's an antiderivative. Then what you do is you evaluate the upper limit, which is b. Then you evaluate that antiderivative at the lower limit. Then you subtract the results. Now I'm going to run through some stuff with that just kind of as review material here today and kind of talk about why we do that. Sometimes I can show a few simple examples that would show why you do f of b minus f of a, because it represents an area under the curve bounded by the x-axis, okay? So let's go ahead and just do something kind of simple. This is a real simple example. This is about as straightforward as it's going to be. And what we're doing on this is we're doing the definite integral 60x minus 60x squared. That's a quadratic function. I went ahead and just took a snapshot of a picture from a graphing calculator what that area would be. So you would actually be looking at this area under this curve above the x-axis and below the curve like that, okay? So first of all, what we want to do on this, when we do this, we're going to go ahead and we're going to just do the indefinite integral. So one thing that you learn how to do, and you can do this integral in your head. You don't have to do everything I'm doing, but just to remind you, if you do an integral of a sum or difference, what you can do is you can break it up into two parts, and you can do this. You want to remember these little features of an integral, because sometimes you have to do them. This is an example you can do in your head if you got it down from Calc 1. Okay, do you guys remember what you can do with a constant in an integral? That's another important thing. You can bring it out. Okay, so I'm going to write this as 60 times the integral of x dx. What is dx, by the way? Usually students don't really know that too well in Calc 1. It's a differential. What it really represents is it's a notational thing. It's really representing like an infinitely small width of a real small rectangle. Because what you're doing when you learned about Riemann sums in Calc 1, you learned that you're really doing, when you're doing an area under a curve, you're doing a sum of rectangles. But when you do the integral, the width of that rectangle becomes infinitely small. It doesn't go to 0, it just gets as close to 0 as we want it to go. That's what dx is. Because really this is like the height is what the function is, and then the width is what that is. So it's notation, okay? So again, we can bring the 6 out. So we have 6 times the integral of x squared dx like that. So those are fundamental things that you learn to do with integrals. Break sums and differences up and bring constants out. Okay, so here's the next thing you want to remember. You have what we call a power rule for integrals. Okay, so let's see if we remember that. So we have the power rule for derivatives. Everybody should have that down. What's the power rule for an integral? You do n plus 1, and then what do? divide by n plus 1. You add 1 to the exponent and divide by the result. That's the idea. So that's going to be x to the n plus 1 divided by n plus 1 plus c. That's the power rule that you have for integrals, okay? So keeping that in mind, this is x to the first, so what's that? X to the second over 2, right? Okay, bring down the 6. What's the integral of x to the second? X to the third over 3, okay, like that. So that's it, okay? Now what you'd want to do is you would want to simplify whatever you can. 60 over 2 is 30, so that's 30x squared. 6 over 3 is 2, that's 2x to the third. Now that's the antiderivative, okay? That's the capital F part of the function. Then what we're going to do is we're going to evaluate this integral. So I usually write this like this. That's our antiderivative. Now we're going to evaluate it. So what you do is you start by plugging in the 10. Now you could, if you wanted to, take a common factor of 2 out of that. I'm just going to leave it alone on this problem. I don't think it makes that much difference. So I'm going to have 30 times 10 to the second minus 10 times 10 to the third minus, and I love it when zeros there. I don't know about you. Okay, that makes everything so nice. Okay, so I got a 0 there and a 0 there like that. So that's what you're doing. That's the fundamental theorem of calculus part, is you're evaluating that derivative. Okay, does that look familiar? Or not the derivative, the antiderivative. Okay, so this would be then 30 times 100. Okay, this would be 2 times 1,000. And then this whole thing over here, of course, would be 0. So if you can do that in your head, obviously you do that in your head. So it looks like this is going to be 3,000 minus 2,000. So it looks like the answer to that definite integral is 1,000. So what does that 1,000 mean? It's the area under the curve. And that's the precise area under that curve is what that is. Okay, does that make sense? Okay. All right, let me pull up my graphing calculator here for a second and show you something on this. You may or may not have learned this in your Calc 1 class, but man, you want to know this. You want to, you know, when you're dealing with problems and if there's some technology out there that will help you to be able to check your answer, then you definitely want to take advantage of that. So I'm going to pull out this calculator here, and I'm going to show you how I can check the answer on this. It's really a nice thing to learn how to do. So I could plot, let's see, what we just got through looking at was 60x, and then what was it, minus 6x to the second. Okay, like that. Now I'm going to graph that. When I set up my window, I think my window went, if you look at the graph on your notes, I think it went from 0 to 10 on the x-axis.
0 to 150.
And then it did what? 0 to 150. Okay, thank you. So 0 to 150. We can scale that maybe by 50 and so forth like that. Nope, not like that though. Don't put it in like that. So we're going to go 150 and then get that scaled like that. So then if I type graph, you know, I'll have the same curve that was on your handout like that. Okay, so if you want to check your answer, and this will come in handy in this class quite a bit, what you do, write this down if you need to, you go second trace, and if you go second trace, there will be option number 7. What that is the definite integral. So if you just get that 7 to come out, what it's going to do is it's going to ask you for the lower limit. So on that integral, we were integrating from 0 to 10, right? So we go 0, like that, put the upper limit in 10, and to me this is so cool. I just go crazy when I see this. I didn't have anything like this when I was a student. So it's just basically shading the area, and then 1,000 should come out. So you've got the ability to tell if you're right when you do a definite integral. Okay, so that's something you would definitely want to take advantage of. Use your calculators to kind of help you with that aspect. You want to be able to do it mechanically and with technology. Those of you who are going to go into engineering, once you get into the profession, you do technology a lot more than you do by hand stuff, but you do by hand stuff because you have to learn this stuff, right? That's the only way you're going to learn it. So I kind of want you to have a combination of some technology along with doing stuff by hand. Okay, how's that problem look to everybody as just kind of a review? Okay, that's a pretty basic one. Now I'm going to go on and do one with a trig function. Okay, so I'm going to go ahead and work, this one out mechanically and everything. So the first thing you have on this, you have a definite integral, so you could take the 3 out. That's a constant. So you would have 3 multiplied by the integral from 0 to 2 pi of the sine of x dx like that. Okay, so one of the things that you want to know, that handout I had you pick up that had derivative rules, the trigonometric functions are going to show up all the time in this class. So a couple of things you want to remember is, okay, what is the, let me write it this way. What's the derivative of the sine from your background? Okay, that's cosine x, right? What is the derivative of the cosine? Yeah, okay, that's negative, can't write that right, negative sine x like that, okay? So if you're doing the integral of a sine, what do you take a derivative of that would give you a sine? You got to be careful, that's negative cosine, okay? That's an integral rule that you want to know, but if you know these two things here, you can figure it out. See, if you did a derivative of negative cosine of x, well, we know the derivative of the cosine is negative sine, right? But then you would have that extra negative, so you'd be back to a sine. So what you would get with this then is you would have 3 times, and then that would be times negative cosine x. Then you're going to evaluate that from 0 to 2 pi, like that, okay? Right? You can write this now, if you want to, as negative 3 cosine x going from 0 to 2 pi like that, okay? Now, what's going to happen on this one now is when you do the fundamental theorem, the constant can just be written down, and then you can do the evaluation inside of a big bracket, okay? That's just as well to do it that way. Or you could do the negative 3 with both parts, but you're less likely to make mistakes if you just have that 3 out of there, okay? So now what we do is we do the cosine of 2 pi minus the cosine of 0 like that, okay? And don't go looking for your calculator. When you see cosine and sine coming up, remember that unit circle and trig that your teacher made you memorize? There's a reason why you were required to memorize that, because it's going to show up over and over and over again in calculus. So basically, just a quick review, that's 0, that's also 2 pi, 1 lap around the circle. On the unit circle, the point is 1, 0, right? Okay, so what's the cosine? It's the x value, it's 1. What's the sine? Okay, it would be the y value, 0. So what you'd have is negative 3 here. The cosine of 2 pi is that value. Okay, cosine of 0, well, 0 and 2 pi are the same thing, so it gets this. So you'd have negative 3 times 0, so you get an answer of 0. How many people knew the answer to that problem is going to be 0 anyway? Yeah. Okay, good. All right. Now, I went ahead and did the mechanics of that because I wanted you to see that. But what happens on this, another thing what we'll review is this part of the integral right here. Since that area is above the curve, that part of the integral would be positive. So if you did the integral of 3 sine x dx and went from 0 to pi, you would get a positive answer, okay? You would actually get 1 on that, I think. So, no, you'd get 3 on that is what the value of that integral would be. And then if you did this part right here, if you did the integral from pi to 2 pi of 3 sine x dx, you would get a negative answer. But what you'd end up getting, really, you would get 3 here and negative 3 there if you worked out the details, right? And they'd cancel out, okay? Does that make sense? Okay? All right, any questions so far then about anything? Okay, yep.
So you use trigonometric functions a ton in your calc courses?
What's that?
You use trigonometric things, cosine, sine, all of that, through the majority.
Oh, yeah.
Most schools don't, or a lot of universities don't when they go to calc.
In calculus, I'll tell you the way it works. If someone takes business calculus, there's no trig.
I took engineering calculus in Syracuse. We didn't use trig.
Just depends.
And then
we use it here, though, for sure.
Yeah. So do you guys only use the pi functions, pi 0, 2 pi, or do you guys also? It can
be anything. So anything on a unit circle like pi over 4, pi over 3, pi over 6. If it's not on a unit circle, then you're forced to use your calculator.
Yeah. Exactly.
Okay. So a unit circle will show up with trig functions. Most of the time, the problems that I go through in class and on your homework are designed to go to the unit circle for simplicity and to help you build up your arithmetic skills. That's kind of the idea. Okay, let's review one more thing and then we'll take our break. So the other thing that I wanted to look at, this material right here on the even and odd functions, is from your background, This is stuff you learn in college algebra. You review a little bit in Calc 1 and Trig. What is an even function graphically? What does that look like to you? It's symmetric about the y-axis. Okay, that's what even functions are. How about an odd function? Symmetric about the origin. Okay, so for instance, an even function, an example of an even function, the simplest example I can give you would be like f of x equals x squared. Okay, which is a quadratic. If you graphed a quadratic function, the points on this quadratic function would be like 1, 1. Another good point would be 2, 4. And over here you would have negative 1, 1, and negative 2, 4 like that. So what an even function is, the way you want to learn this is whenever x is opposite, what's the deal with y? It's the same. Okay, so notice when you have 1 and negative 1, well, those y values are still 1. Okay, same thing with negative 2 and 2. Notice when x is opposite, the y's are the same. That's what an even function is. It's opposite x gives same y. Okay, however, if you have an odd function, it works like this. The simplest example for an odd function would be like y equals x to the third, where you have something that kind of looks like this. Points on this function would be like 1, 1. You would have a point 2, 8. 2 to the third is 8. Then if you would have negative 1, negative 1, and you would have negative 2, negative 8 there. So what's the deal with an odd function? When x is opposite, what's y? It's opposite also. Okay, that's what odd functions are, and that's the way you want to learn that, is even functions just mean opposite x, you still have the same y. Odd functions mean if you have opposite x's, you have opposite y's. And that's what gives the symmetry. Does that make sense? Okay. So what it means to be symmetric about the origin just means like if you took this shape and folded it over y, then folded it over x, they'd match perfectly. Okay, so it just takes two folds, where of course y-axis symmetry is just fold over the y-axis. Okay, so you deal with even and odd functions quite a bit. So here's what the theorem is. If you have an even function, if you know your function's even, if you integrate from negative a to a, now those limits have to be the same, then it's just going to be double the integral. Okay, and I'll explain on the next page. I have a good example visual that'll help you understand that. So you would go, if you doubled the integral from 0 to a, it's easier to do the problem that way because isn't it nice to have 0 as a limit of integration? Yeah, it's easy. It makes everything easy. Okay, here's an even easier one. If you have an odd function, if you integrate from negative a to a, you're going to get 0. Okay, so if you look at the example that I did on B, that's an odd function, isn't it? Okay, and that's what ended up happening on that. A sine wave is an odd function. So in part, that's not exactly why that canceled out. It's partially why that area canceled out. So here's what I want to kind of do is just these examples on even and odd, then we'll take a break here. Now these are pretty easy to do. Okay, so first of all, you don't want to just take a guess if it's even or odd. You want to remember how you do this. So if you want to figure out if something is odd or even, here's what you do. You start off with f of x, in this case, is equal to x squared. And you don't really want to have to rely on your calculator to tell it's even or odd. You want to rely on math. So what you do is you basically just figure out what f of negative x is. See, the idea is you're interested in what happens when x is opposite. Okay? So if we did that, here's what we would do. Okay? We're doing x squared. What we do is we do negative x squared. Well, what happens if you take a negative number and square it? It gives you positive, okay? So see, here's what happens. When you had an opposite x, what happened to the y? It was the same. So anytime that opposite x provides the same y, that means that you have an even function. Okay, that's how you know that. So you're always looking for when you substitute x with negative x, you're seeing if it's the same. If it's the same, it's odd. It's even. If it's opposite, it's odd. If it's neither, it's neither. That's the way it goes. So what you could do in this problem, instead of integrating it this way, what you could do is you could double the integral and then go from 0 to 3. Okay? You don't have to do it that way. I mean, you could just crunch out the integral and do it that way if you wanted to. Okay? You could just go from negative 3 to 3 and you'll get the same answer, but this is a shortcut. Okay? All right, so when I do that then, what I would have is I'd have 2, the antiderivative of x to the second, what is that? X to the third over 3, right? That's your antiderivative, okay? And then see the 2 is just the constant there. Then I can go through and evaluate this from 0 to 3, okay, like that. Okay, well 2/3 is a constant, so you can just write 2/3, and then you can evaluate the upper limit, so you'd have 3 to the third minus 0 to the third, so that's 2/3 times 27 minus 0, and then you can cross that out. 27 over 3 is 9, so 2 times 9 would be 18. So what you would end up getting on that problem is you would get an answer of 18. Okay? If you did the antiderivative, which again is x to the third over 3, and evaluated from -3 to 3, you certainly get the same answer, but a lot of times that simplifies the calculation. And if you can find an easier way to do something, well, that's what you want to do, right? Okay? All right, does that make sense to everybody? Okay, so what happens on this is really this is a graph of x squared. So really this region in here would be 9, and that would be 9 right there. So that's why you're doubling that, see? Okay, it's symmetrical, so that would be the idea. Okay, does that look okay? Okay, all right, now let's see this one. This one is if you have the function that you're integrating is f of x equals x cubed, what you want to do is figure out what happens when you do f of -x. So if you do that, you replace this x with a negative and you cube it. Okay, fundamental stuff. What happens if you take a negative number and raise it to the third power? It's negative. What if you raise a negative number to an odd power? It's negative. Okay, that's important. That's important algebra. So that is negative x to the third. So see, here's what you found. You found that when x was opposite, you found that the y value, or the function value, and I forgot to put my negative there, those things were opposites, weren't they? So what does that tell you? It's an odd function. Okay, it's an odd function. Okay, so if it's an odd function, and the thing is the limits of integration have to be the same, okay? So, I mean, one's -3, the other one's 3, so the answer is what? Okay, saves you time, doesn't it? Okay, so you want to be able to see that. And what would happen in this particular integral if you did this? You would find that this area in here, if you did the integral from 0 to 3, that would give you a positive answer. And then if you integrated from -3 to 0, that would give you a negative answer. And you can see those areas are symmetrical. So what happens? They cancel each other out. That's the idea, okay? So that's one of the things you want to do is take advantage of this when it shows up, okay? How's that look to everybody as a review? Did you learn a little bit of this in Calc 1? Okay. All right, let's see. Let's go ahead and do a break now for 10 minutes. Let's just come back at 9:25. And then we'll come back and we'll finish this thing up. So what I'm going to do is do a trigonometric function now. So a couple of things that are kind of important on this is I'm going to look at something with this unit circle here in just a minute. But something that really is nice to know is certain trig functions are odd and certain ones are even. And you can tell by the unit circle if you ever forget. So the ones that are even, there's only 2 of them, are the cosine and the secant. Those are even functions. Now, if you look at this unit circle, the unit circle would clearly tell you why those are even functions. So like if you can see this okay, the idea would be, remember the cosine is the x value. So if you're doing the cosine of pi over 6, that's square root 3 over 6. So notice on this, what happens if x is opposite? Okay. Yeah, the y value turns out to be the same on this then. So what happens is, what happens on a cosine is on this, if you have an opposite x, you're going to end up having the same y value like that. Okay, that's what happens on that. Now, if you look at your odd functions, like an odd function would be like a sine is a y value. Okay, so notice on this, if you have an opposite y value on that, okay, then that's what's going to give that an odd function is symmetrical about the origin. So if you look at this, this point and this point are symmetrical about the origin. They have, when you have an opposite x, you have an opposite y. Okay? So that's a sine wave is going to be an odd function for that reason. Whereas a cosine's an even function, again, because these 2 points right here are symmetrical about the y-axis. So opposite x, same y, like that. So what you want to know is, and it's helpful to just remember this, the way I remember it is, the cosine and secant are even, everything else is odd. So your odd functions would be like the sine, the cosecant, the tangent, and the cotangent, like that. Okay? So those are your even and odd functions. The other way to remember that is to remember the graphs. So one thing that's a good thing to do is review the graphs of the 6 trig functions as well. Okay, so in this particular problem here, when I do this integral, you know, there's a couple things you can do. You don't necessarily have to do this. I'm going to pull the 5 out, so I have 5 times the integral, negative pi over 2 to pi over 2 sine of x. So what you're trying to learn is look for shortcuts. Now the key thing to me is the limits of integration are opposite. So that kind of clues you that maybe something's going on this problem. Okay, a sine is an odd function. So if it's an odd function, then what's the value of that integral? 0. Okay, so the answer to this problem would be 0. You would just have 5 times 0, so you would be 0, like that. Okay? Now, the reason that this is an odd function, again, is if f of x is equal to sine x, don't worry about the 5. If you do f of negative x, then you're doing the sine of negative x. Okay? And what happens when you do that is you end up getting negative sine x. The unit circle explains that. See, for the idea would be like if you have, here's a sine right here. The sine of pi over 3 is square root of 3 over 2. But if x is opposite, okay, then what happens on this, you end up having an opposite y value there. So what happens is, if you did like, say you were doing you had the sine of pi over 3. What would happen if you had the sine of negative pi over 3? Negative pi over 3 is clockwise, so what you want to notice on this is this value and this value are opposites. So the idea is if the angle is opposite, so is the y value. So it's an odd function. That's y, okay? So that's why the value of that would be 0. Does that make sense? Okay? So you want to know which trig functions are odd and which are even, and then that'll help you when that shows up. Okay, let's take a look at a couple more of these, and we want to get in and review the U-Substitution a little bit here. Okay, this one is, if you look at it, what do you think it has? Even or odd? Okay, yes, you see an even exponent. There's a good chance that it's even just because of the even exponent, but not necessarily. So really, technically, you want to know how to work out the math on this. So f of x is equal to 3x to the 8th minus 2. So if you do f of negative x, you have 3 times negative x to the 8th. This is an easy enough problem. You can reason this out in your head. So what is negative x to the 8th? X to the 8th. The negative number to an even power is positive. So the idea on this would be is the y values turned out to be the same. Okay, so that's why it's an even function. It's not because it's an even exponent. That has a lot to do with it, but that's not technically totally true, so it's an even function. Okay, the other thing is, the clue on this problem is those things are the same. Okay, so how do you break it up if it's an even function? You double the integral from where to where? 0 to 2. Then you work out the integral 3x to the 8th minus 2 dx like that. Okay, and what you're doing is just taking advantage of the 0. And if you forget this, it doesn't matter. You'll still get the same answer if you don't do it this way. Okay, so what I'm going to do on this is bring down the 2. The antiderivative, if you just do this part right here, you could write down the 3. The antiderivative of x to the 8th is x to the 9th over 9. What's the antiderivative of 2? That's one that students forget a lot. When you take the derivative of 2x, what do you get? You get 2. Okay, so that's 2x. Okay, so we have that. Then you're going to evaluate that from 0 to 2. Take advantage of the 0 for the simplicity of the calculation. Okay, so then what you'd have, that would cancel out to like a third. So you would have 2 times, and you could write this as x to the 9th over 3 minus 2x, then you could evaluate your integral like that. Okay, so what I'm doing is I'm setting it up as double the integral from 0 to 2. Does that make sense to everybody? That's because it's an even function. That's the only reason we can do that. So then we would have 2. I'm just going to draw kind of a big bracket. I'm going to plug the upper limit in here. So I'll have 2 to the 9th over 3 minus 2 times 2. And you don't really have to write this part out necessarily, but if you plugged a 0 in, you'd have 0 to the 9th over 3 minus 2 times 0 like that. And of course that whole thing goes to 0, so that simplifies the calculation. Okay? All right, and let's see what we got from here then. 2 to the 9th, I'm going to use my calculator. I don't remember what that is. So it's what, 512? Okay. So that's going to be 512 over 3 minus 4 like that. Now when you do definite integrals, get used to it. You're going to do a lot of arithmetic. Okay. Sometimes the hardest part of a definite integral is all this arithmetic you got to do. So you got to get a common denominator on that, because 512 divided by 3 is a decimal. You don't want to go to decimals. We want to get exact values. So I have a common denominator of 3, so I'm going to have 512 over 3. I change this by multiplying that by 3 over 3 to 12 over 3. And then that's going to give 2 times 500 over 3. Okay, then you can just multiply straight across and get 1,000 over 3 like that. So that's your exact answer to your problem, is that. Okay, all right. Now, if you get into a pinch, I want to remind students of something on my graphing calculator, because this is sort of a helpful thing to do and know something about. Like on a graphing calculator, if you get into some really heavy arithmetic, because you will in this class, I mean, you could do this. You could go like 2, this is not cheating, it's using technology, but you want to be able to do it both ways. You could do 2 times 512 over 3 minus 4, just typing it exactly as it is, and that'll give you a decimal, and then you have this math button that'll convert it back to a fraction. So if you go math and then frac, voila, there we go. That's kind of cool, isn't it? Okay. Learn to do that too, because you're going to make mistakes. You will see me make mistakes on arithmetic too, because a lot of times I get in a hurry and it's easy to make mistakes on arithmetic. So check with your calculator, okay, using that math frac tool, okay? All right, let me just ask a question on the next one. Do you know what the answer is? Yeah. 0. It's an odd function, okay? A sine's an odd function again. That's equal to 0. Again, those limits of integration are going to be symmetrical like that. Now, technically, the way you show, because a lot of times students just assume it's an odd, and you want to be careful about this. When you're doing the sine to the 5th power, it's really the same as that. It's the sine, the whole thing to the 5th power. If you do f of negative x, then what you're doing is you're replacing this x right here with a negative x to the 5th power. Now, one thing you learn in trig is you learn what are called even and odd identities. And an identity for sine of negative x, since it's an odd function, is it's equal to that. Okay, so this whole thing right here technically gets replaced with negative sine x to the 5th power like that. Now, what happens if you take a negative number and multiply it out 5 times? You get a negative number, right? So technically, that's why it's an odd function, is because this really turned out to be this. And I'm going to put the 5th power back like that. So see, there's the original function. Here's the final function. It just turned out to be an opposite. Does that make any sense? Okay. This is called an odd identity. If you had an even identity like a cosine, it works like this. Cosine of negative x is equal to cosine x. That's how even functions go. So if you're going through and mechanically figuring out if something's even or odd on trig functions, pull out those identities. Okay, and they're easy to remember. I just try to teach students even functions mean opposite x, same value. Odd functions, opposite x, opposite value. And that helps you remember the identity. Yes?
So if it was like sine to the 4th, would it be even?
Yes. Yeah, see, that's why you got to be careful about that. Even though the sine itself is an odd function, it's the power that made the difference. Okay, that's the idea. So you got to be cautious on that. Okay, let's go to the next page and do a couple of U-substitution examples. Then I'm going to start you off a little bit into chapter 7. We go to 7.1 because it's integrals, and we just go ahead and do mostly U-substitution and some different types of integrals. Then we go back to chapter 6 where we focus mostly on applications of integrals. Okay. All right. So U-substitution. If you didn't know about U-substitution, your only choice would be to multiply x squared minus 1 out 99 times by foiling and then doing the power rule. Okay. So you don't want to do that, obviously. U-substitution, and sometimes students do not get this down at the end of Calc 1 because it's the last thing you usually learn. What you do is you choose something for U, and what I'm going to do is what I highlighted is going to be the U, and it takes practice. There's going to be a lot of times when you're going to choose that wrong. Okay? Now here's the idea. The remaining part of the integral is 2x dx. So the idea is you would like du to be the rest of the integral. If it's off by a constant, you can deal with it. So what is the derivative of x squared minus 1?
2x.
2x. And then you got to put your dx. That really kind of comes from chain rule. You're multiplying it by the derivative like that. So that's U-substitution. So what you have is this thing right here that I have highlighted in yellow. That's the u part. Okay? And that would end up being u to the 99th. What's the integral of u to the 99th? U to the 100th over 100, that's a piece of cake, right? Okay. Now this part right here, the part in blue, that's the du part right there. So you've got everything absorbed with substitutions. So what you do is you do the integral of u to the 99th, and then the 2x dx is going to be the du part right there. So you got to make sure you do a u-substitution that everything is accounted for. Everything must be accounted for. The trick is whatever you pick for u, du needs to be what's left over. Or maybe it could be 5x dx instead of 2x dx because we could still deal with it then. We can handle it if it's off by a constant. So then what you would have is that integral would be u to the 100 over 100. It's an indefinite integral, so that would be plus c. And then the last thing that you got to remember to do, and this is real important, is whatever you have for u plugs back into the final result. So what you would have as an answer in is you would have x to the second minus 1 to the 100th all over 100 plus c. That would be one way to write that answer to the integral like that. Okay? Now, one thing that you want to be able to do on this too is get in the habit of when you do integrals, unless they're real complicated, of quickly checking the answer and making sure you're right. So if you did this, see this 100 is a constant. That's really a 1 over 100. So if you did the derivative to check, you would have 1 over 100. Now, when you do the derivative of what I'm circling there in green, that's a chain rule. So you'd bring down the 100. You would leave the x squared minus 1 alone. And then that's 99. But then what do you got to do by chain rule? You got to multiply by the derivative of what's inside. So what's the derivative of what's inside? 2x. Good. Okay, so what you have then is this. The hundreds cancel out. Why am I right? Well, that's the problem that we did. Okay, so that thing right there matches what we did at the very beginning. So see, it's real easy to tell you're right on an indefinite integral most of the time. Okay? All right, how does that look to everybody? Okay, well, that's good. You're going to get back to the swing of doing U-substitution this class, and you're going to do it a ton. Okay? So when I look at number 2, you always want to think, well, what kind of integral do I know? What if you had the integral of e to the x? Do you know what that is? I hope so. That's the easiest one there is. It's e to the x, right? Okay. So you're going to probably, if you see an e to the x, there's a really good chance that you want to turn this into e to the u. Okay. So what do I want to set u equal to, you think? X squared. Okay. So we're going to let u be x squared, because we would like to turn this probably into e to the u integral. Okay? Now, what's left over is x dx. So we're hoping that du is x dx or something real close. Okay, so what's du? 2x dx. Okay? So it's close. So here's what you do. When you have the statement du is equal to 2x dx, you can divide both sides by 2. So you could write this as 1/2 du is equal to x dx. Okay, now you've got everything absorbed. So this stuff you see in yellow, that gets replaced with not du, but 1/2 du. That's how you handle it if your integral is off by a constant. Okay, so whatever u is, du has to be the rest of what's left over. Does that make sense? Okay, so your integral goes like this now. So you're going to have the integral of e to the u, and then x dx gets replaced with 1/2 du. And that's an integral you like, because it's easy. Okay, you can bring the 1/2 out. You don't have to do that. You can tell me what the answer is in your head on this one. I don't care. So you get that. Okay, then what do you do as your last step? Plug u back in. U was x squared, so that thing needs to plug back in there to get the final answer. So your answer would be 1/2 e to the x squared plus c. Okay, like that. That's a U-substitution integral where you're off by a constant. Okay, does that look okay? Could you do a derivative of 1/2 e to the x to the second? Okay, the way you would do a derivative to check is just this. Write down the half. The derivative of an exponential is itself. However, the chain rule tells you to multiply by the derivative of the exponent. Notice the 2's cross out. You're back to x e to the x squared, which is what the integral was in the first place. So you're right. Okay, so be sure that you have that ability to check and verify you're right. That's a super important part of learning calculus when you're doing integrals. Okay. All right. Any questions on anything? Okay.